Good day. So let us continue our lectures on the neural networking and deep learning. So it is the second lecture registration. In the first lecture, we have considered the general principles of neural network construction. The interesting fact is that in the build a neural network of a good topologies, then we should adjust its parameters, weighting, which are weighting coefficients and biases of the nodes. So such a procedure is called learning procedure for the simple networks without big number of hidden layers, and it is called deep learning when it deals with neural networking topology with one or more intermediate, so-called hidden layers. The role of input and output layers are very clear. Input layers are designed in order to introduce the input information to the networking. For example, in the problem for handwritten digits recognition, it is 700 and more than 700 pixels. Yes, then we have subdivided 28 by 28 our handwritten box. So we have a big number of input nodes. The output correspond to the question which we need to ask the neural net. For example, for digit recognition should be 10 output nodes, yes, which correspond to 0, 1, and so on, up to 9. So 10 nodes. And very important that the role of hidden layers is to analyze a subset of input information. So it is fragmentation of our information of our task into n subtasks. So every new hidden layer can detailize this information. So in such a way, a neural network can construct some very sophisticated classification and to study the problem in very profound mode. As a result, the neural net, by simply adjusting its parameters, if correctly defined, and if they work in the line of the statement of our problem, yes, if they correctly correspond to our statement, then the neural net will autonomously construct some algorithms by using Boolean functions. We have seen that, for example, NAND, yes, the fundamental Boolean function which generate all other functions, and some complexity around this elementary universal operation. The neural net can construct very complicated and very sophisticated algorithms, Boolean algorithm of analyzing without that we can even understand profoundly what happened. And such a procedure, if we impose the basic topology and begin to start a correct procedure of parameters adjustment, then the neural net can give us very interesting and very unusual solution on our problem. And the big value of neural network is that neural net resolve the problem without possibility of rigorous formal formalization in mathematical way. So when we have some fuse system without very precise definition, and when we have, if we have some fuse problem, yes, for example, to distinguish male face on female face, or to distinguish cat and dogs. So we should recognize some patterns which are very, very similar, but by pattern recognition we can do it. So it is a big advantage of neural net. So let us begin now on the some basic principles of the learning process. Yes, the learning process. So first of all, sigmoid neutrons. So we have some training procedures basing on the sampling of learning patterns. Yes, for example, sampling of handwritten digits. Yes. So and our procedure to learn the net is our procedure needs that we have these procedures. We have to provide these procedures in very smooth mode. In smooth mode seems significant that the small increments of our parameters imply the small difference of the cost function, and cost function is fundamental criterion of training. So the cost function is nothing else that mean square value of error of the network, yes, in recognition, and we need to tend to put to zero as close as possible the cost function as a criterion of learning at the finish of the learning procedure. So again, we have some input W plus delta W. Yes, it is our generalized parameter, that is weight, coefficients, and biases. We have generalize it in a big vector W. Yes, so we have some vector W plus delta W. So, and we should have small change in any weight or bias will imply a small change in the output of our neural net. It is an important criterion of correct learning of the neural nets. So also very important the general view of our cost function, which we shall repeat what is it, but important that such cost function we especially choose as a quadratic function. It's a quadratic function. It is a very good function. It is a smooth function, double differentiable function, and it permit us to find the absolute minimum of such function. At least some regular procedure to look it for. For example, let us say that the network misclassified an image 8 when we should have been 9. So it is very similar but different, and we have error of our output. So we should figure how to make some small change in the sense that when we teach, for example, when we learn 8, then we have not error in 9 and so on. So the new learning procedure should not create the error of the previous learning procedures. So, however, it is not very easy task, of course, and so to solve it, so first of all, we should adjust this coefficient, not directly, but using some special, very smooth function, for example, sigmoid function, or so-called logistic function. So sigmoid neuron are very similar to perceptrons, but perceptrons work in binary mode, so it can assume only two values, yes, 0 and 1. So our so-called our function of evaluation should have a jump at zeros, from 0 to 1. But the sigmoidal function is a very smooth function which provide us to get small increments of the bias value, having small increments of the entry values, yes, our weight coefficients and the biases in the previous layers. So now we depict these sigmoidal neurons very similar as we have depicted the perceptron, but so we have also n input, for example, x1, x2, x3, generally n input neuron inputs, and we have one output from this neuron. But instead of being 0 or 1, yes, it can take any values between 0 and 1. So it enlarges our possibilities for learning. This the weight parameters, yes, W1, W2, and so on, and the overall bias B. So but output is not now binary, but instead of it, we calculate Wx plus B as before, but then we take a value of this, it is the value of function by this argument, yes? And the function is sigmoid function or logistic function, 1 divided by 1 plus exponential minus z. Or in coordinate form, we can rewrite it. Okay. The form, the shape of our logistic function is very similar to very similar to the shape of, for example, Gaussian distribution function. Very similar. So the difference between sigmoidal perceptron and sigmoidal neutron is, for sigmoidal, it is output. This output is take some value between 0 and 1, and for perceptron it is binary, has some binary value. So the smoothness of sigma means that small changes delta wj, yes, the weights and the biases, yes, will produce a small change output in the output from neuron. So delta output is about the output by partial differentiation by weighted coefficients delta wj, yes, by the direction wj, and we make some summation on all j plus partial differentiation of partial derivative of output by bias argument multiplied by the increment of the bias. So delta output is a linear function depending on the weights and the bias delta B, delta W and bias delta B, as we have seen before. Okay, this is one that is one can achieve any desired small bias in the output by moving the parameters. Okay. Now let's consider the architecture of the neural networks. Consider the following network. For example, one input layer, then one hidden, and one output. It consists of input layer with input neurons, yes, 3 input neurons. Then output layer contains the output neurons, or as in this case, a single output, and hidden layers, not an input and nor or an output. Yes, it is intermediate layer which analyze some segmental detalization of information before to take a decision. So the network more profound, for example, for more than one hidden layers with input and with output layer, is called multi-layer perceptrons or MLP. But it is really consists of sigmoid neurons, not perceptrons, but historically such notation is fixed. So a simple network to classify handwritten digits. Let's return to our the problem of handwriting recognitions. Having the specimen, so some postal index of United States, yes, 504192. First of all, we should break this image into separate boxes, and then we should singularly to recognize any digit. It is so-called segmentation problem. Before it was resolved by using some written boxes on the envelope, on the postal envelope in the United States. Then now it is not a problem to do it automatically. Once the image has been segmented, yes, then one need to recognize any place, any box, which value of handwritten digit is written. For example, such box, the first is 5. To recognize individual digits, we use a 3-layer neural network, and it is enough for this aim. So input layer 784, yes, 28 by 28 pixels, yes, of any handwritten digit box, yes. Then so it is very large. It is very large layer. Now we have reduced for evidence. Now we pose some hidden layer, yes, with only 15 neurons, and it is enough for such type of problem. And we have output layers 0, 1, 2, 3, and so on, up to 9. So 10 output layers. So as we told, these digits are already prepared, and one can download it from internet. It is open information, and it presents not only the collection of 60,000 different mode to handwrite the digits, but also the division of the boxes in 784 input neurons. So we have a very long chains of pixels, and these pixels are expressed in grayscale, so they express it of some black and white grade, yes, with a value 0, 0 representing white and a value 1, 0 representing black. And all intermediate represent gradually darkening shades of gray. The second layer is a small hidden layer containing just 15 neurons. So we can take 15 segmentation inside our handwritten box, and to make some possibility, some deeper analysis of patterns inside of the patterns inside our handwritten boxes. The output layer contains 10 neurons. If the first neuron fires, that is, has an output about 1, so our neural network decided that the zero digits fires, so with probability about 1, it is recognized the digit that the digit is 0. The second correspond to 1 and so on, and the tens correspond to 9. So now the question is why we use 10 output neurons. For 4 neurons should be enough because two at force 4 in grade 4, yes. So binary digits in 4 position can codify 16 different numbers. But we in this situation we have 6 extra, yes, extra values which we don't need, and we have some confusion in the course of training our network. So such symmetricity and symmetric analysis is very important for successful deep learning and have good performance in the sense of precision of recognition. So such explaining why not 4 output but 10 output nodes. We have already intuitively, yes, heuristically explained, but it touch very important thing. What are those hidden neurons doing? They make some sectioning of the part of image and begin to observe some patterns, yes, some sub-patterns which contain a handwritten box. So, for example, the first hidden layer give us such fragment, the second also such. So it is very near to have 0 image of 0 handwritten pattern, and in some sense it is the unique possibility. So our neural net should elaborate the response that it is 0. So if, for example, we have only 4 output neuron, should be very big confusion of how to recognize and to appropriate it to adjust reply. We have some confusion. So for us, symmetricity is very important thing. Of course, there are also asymmetric neural nets with asymmetric topology and so on. But it is particular case, specially designed for particular problems, and we can discuss it later. Why one can consider some incomplete or non-symmetrical neural nets. So learning with gradient descent. So very interesting thing is having a big set of training our neural net for example, which contains for training 60,000 images, yes, that can be used as training data. And then we should keep, without training, other 10,000 images to use as a test data. If they are very good mixed, like image between such training set, yes, 60,000 training sets. So if we can easily recognize such number of digits which have not participated in the training procedures, then it can mean that we have learned a good configuration of a network which have some very good recognition of handwritten digits. So again, this is a small subset of these digits, specially collected by American Institute of Standards and distributed it now free distribution for the training of digit recognition neural net, and it is now since it was a first success of neural net for use of neural nets, and it is a classical example, classical example of a complex, enough complex problem statement in the neural net. So now let us introduce some parameters for the SQL networking learning. First of all, input parameters X. Yes, it is pixels from our handwritten boxes. So any handwritten boxes is divided by 28 by 28, so 784 values of vectors of different values from 0 to 1, which reflects the gray scale of the pixels. So we have some training set. We have the input X, for example, 3, 4, 1. So we can choose and this set, pixel set, correspond to some input X. Then the desired output, Y of X. What is it? For example, taking 1 or taking 1 or taking this one or taking this one or taking this one. The desired is 1, So it is 10-dimensional vector. What is 1? 0, correspond to 0. The second node, 1, correspond to 1. The third, 0, 0, 0, 0. See? 0, 1, 0, 0, 0, 10 times. For example, if correspond to 6, so 0, 1, 2, 3, 4, 6 at 6 position should be 1, and so on other 0. And this is vector transposition. From the row we obtain the column vector, and then we introduce such very interesting cost function. It is our square error. You see, the desired output, Y of X, so something like this, minus A. A is vector of outputs from the network when X is input. So we have some not just correct coefficients. So we have some result, and we have, what is it? It is norm, square norm, and this norm is so-called the Pythagore norm. It is so-called length function of a vector. Yes, so the length function by all the components, deviation from the desired value and the value which we have obtained by calculating our neural network. So you see, we should have in this case some uniformity by all the components. It is very, very wise, very, very clever normalization. Yes. So if we have all places the increment is very small, but in one place the increment is very big, it is not good procedure of training. So we should exclude absolutely some pathological value of one or two components which can imply some jumps in our procedure. We have not, and we don't have, we must not have some jumps in the procedure of learning. It is very important. So we should have some smooth procedure of teaching. So now let us introduce some notations. So W, all weights or in our network, yes. So WB. So implicitly it presents here B and W. But B all the biases. Then we shall, of course, we shall precise such W and B. So now it is some strings, yes, some strings. So one-dimensional vectors of all possible weights and biases. Then we should, of course, present such weights and biases in more ordinate, ordinated view. That is, should be some matrix or matroids with corresponding coordinates of the layers, yes, of the nodes and so on. Layers, nodes. Okay, should be indexed then more precisely, which corresponds to our problem. Now it is a generalized vector or some generalized matrix without precise coefficients. We shall introduce it in opportune manner in the sequel. So N is the total number of training inputs. Yes, N. A, the vector of outputs from the network when X is input. So we put the input X, and then we calculate the response of our neural network, and it will be A. Of course, at the initial stage should be very, very different from our desired vector X. Yes, so real situation. Our aim is having put even casually all the coefficient, and then to adjust this coefficient by using the training samples. Okay. So such function is quadratic function, is smooth function, but you see also it contains some uniformity of deviation by component. It is very beautiful function. You see, very clever function. So with such definition of our cost function, or in other words, the mean square error of the response of our, or the decision or response of our neural net. What is our objective? Our aim, our objective is to make some learning procedure in the sense that the cost value for any W and B, which entry parameter, should assume a value near zero when the desired vector y of x is near a. Yes, it is near our response to these input values. So the aim of training to minimize the costs, so to adjust the coefficient of our neural net in the sense that our cost function should tends to minimum, yes, should tends to minimum by W and B, by the parameter, yes, weights and biases of our net, neural net. So now one proposes the algorithm of gradient descent. Consider now a simple example of a function of two variables. Why of two variables? Because with such big samples, yes, which some big samples of training data, we have a function, a cost function of a lot of big parameters, yes, a big number of parameters. So we cannot image some function, even quadratic function, on several thousand of parameters, but can be millions of parameters. So now we imagine something more simple thing. Mathematically, it means that if we consider two parameters, it is some multidimensional reasoning, yes, two parameters, for example. So we can image some multidimensional function. Once we propose some procedure to approach the finding of absolute minimum of such function, then we can elaborate some mathematical formalism which bring us to any dimension, and having the normal matrix or operator calculation, we have good rules for doing some calculus, and nothing essentially change in this procedure. So first we should have some imagination to find some rule which resolve our problem. Then we can, using mathematical formality, mathematical formalism, pass to the general rule without imagining what is the form of the function in big dimensions which we cannot image. So now let us suppose that we have the cost function, also some quadratic function, yes, which we should bring to minimum by v, and v is two dimensional parameters, yes, two-dimensional parameters. So we should have some paraboloid, and of course we can image how we should find out the minimums, because we have one dimension, other dimension, we can project on the planes, yes, coordinate planes, and consider one-dimensional problem with parabolas. Yes. But let us now consider such function with intents that we should then pass to more dimensions. So let us think the function surface as a kind of valley, So let us imagine a ball rolling down the slope of a valley. Our intuition tells us that the ball will eventually roll to the bottom of the valley. What happens if we move the ball at a small amount delta V1 in V1 direction and in a small amount delta V2 in V2 direction? Then the variation of the value, yes, of our cost function will be as we have written before. So it is so-called gradient representation of the function in yes, gradient representation of increment of a function of two variables, yes, by increments of the variables, gradient representation. So it's very natural. So we shall find such delta V1 and delta V2 for which delta C surely smaller than 0. So the ball rolling down into the valley. And the vector of changes column, yes, our increment, our joint increments, delta V1 and delta V2 transposed. And the gradient of our function C is nabla C, yes? So partial derivative of C by V1 and dC by dV2, also transposed vector. So we can rewrite the variation of C of V as delta C is nabla C scalar product to delta V. Now let us choose especially delta V is minus eta nabla C, where eta is a positive parameter, known as the learning rate. And in fact, for learning neural nets, one should define some parameter of small parameter of learning rate. And so we should learn slowly, but not very slow, but in the best direction. You see, and it is very important. When we have some slow passes to learn, but in the best direction, yes, and the best direction should be, of course, gradient direction. So we have some big success of learning our neural net with good efficient minimizing of cost function. Okay, so delta C is minus eta by this representation. Nabla C by nabla C, it is minus eta nabla C square. So delta C surely less, yes, smaller than 0. So we choose the following increment. From V pass to V prime is V minus eta nabla C. So it is one pass of training, you see, for two parameters, of course. And repeat this operation over and over, we can reach a global minimum. Yes, to make gradient descent work correctly, one should choose the learning rate eta. It should be it should be small enough that that 9 is a good approximation. If we don't, we might end up with delta C bigger than 0, which obviously would not be good. So we increment our error, yes, and increment our cost function. We should minimize. Now we pass 2 variables to m variables. So we have elaborated a good method, and now we can pass it to more dimensionals, and in coordinate form it is longer written, but in operator form it is absolutely the same formula. Okay, so m variables, nothing will change significantly. So now we should put to minimum our cost function with more variables. Yes. Vector of changes also we defined as before. The gradient of the function of cost function is nabla also as before. And the gradient descent iteration is a consecutive application of the update rule, which we have written before, for more variables, but the mathematical formalism is absolutely the same. It is a way of repeatedly changing the position nu in order to find a minimum of the function of absolute minimum of the function c. The rule does not always work. Several things can go wrong and prevent gradient descent from finding the global minimum of C. But usually it works extremely well. So we should make some protection mechanism which reveal some pathological increment of our variation of cost function by variation of our parameters. Introduce the constraint, the signs of the move. So, for example, let us delta V, yes, and the norm is again the Pythagore norm, delta V, yes. So square root of the summation of square components, yes. It should be such a length function, should be epsilon for some small fixed epsilon. So we, for some small fixed epsilon, choose such rate of learning. So proposition 1, the choice of delta V, which minimizes nabla C by delta V, so our gradient expression of the increment of our cost function, is delta V is minus eta nabla C, where eta is epsilon divided by the norm, yes, the Pythagore norm of nabla C. Hint of proof. You can use it autonomously to use the Cauchy-Schwarz inequality. So the gradient descent can be viewed as a way of taking small steps in the direction which does the most to immediately decrease C. And this is very important, that the best direction to move our ball is the the most immediately decrease because we have chosen the gradient direction. So gradient descent closely mimic a real physical ball. It has some advantages because, for example, the ball move with some additional forces, but we constrain our ball to move in the direction of the best descent, and it is very fundamental. Then, very important to mention that it can be very costly operation. Why? Because sometimes we should verify the criterion of minimum, yes, like the second partial derivative of the cost function should be equal to 0. But if there are millions of such Vj, so we need to compute half of trillion million squared, yes, 10 elevated by 12 second partial derivatives. There are tricks to avoid such kind of problem, and in fact the art of deep art and the now the deal to learn deeply a neural net is to reduce the cost, and there are a lot of mathematical facts and mathematical tricks which help to avoid big dimensions. It is very interesting for mathematicians because engineers are constrained to do something to close their practical problems. So they invent some tricks which can drastically reduce the dimensionality as as mathematical model, and also for the volume of necessary numerical procedures, you see. So we can reduce the time for calculation from several thousand years to several minutes. So again, how to apply gradient descent to learn a neural network? To use gradient descent to find the weights and biases which minimize the cost function, which we have introduced before, and it is very clever cost function, you see, such norm. It is really component-wise norm, which does not permit to have some big deviation in some separate components. It is very clever norm. So it is something like cumulative norm. So the gradient vector is now we rewrite it in the terminates of our weight coefficients and our biases of our network. So firstly, we considered the gradient descent method for generalized variable of big dimensions. Now we concretize it divided by weights and biases, okay? So we now rewrite it in the term of our first statements of problem. So now rules of update rules we rewrite in our new, more concrete, more concrete notation. Yes, WK minus eta. Eta we have chosen by epsilon, small enough but positive. Yes, DC by DWK, and the same thing for the biases. This is a rule which can be used to learn in a network, neural network. In order to speed up learning, an idea of stochastic gradient descent can be used. Stochastic gradient descent. So the stochastic mixing is some universal principle which will be used for the problem of deep learning, not only for the speed up the procedure of gradient descent, and it is based on probabilistic law of large numbers. So notice that the cost function has the form, so it is some middle value, yes, mean value of some Cx. So we have training consequently for any x. Yes, we choose from some large set of training set of training learning, our training set for learning our network. Yes, Cx for any training sample x. Yes, and x can be, for example, for digits, it's one of 60,000 different samples. That is, it is an average over the cost Cx. The difference, yes, the deviation between our desired response minus what we have really obtained by training our neural net, having as input the vector x for individual training specimens. Okay, the idea of stochastic gradient descent is to estimate the gradient nabla C by computing nabla Cx for a small sample of randomly chosen training inputs. By averaging over this small sample, it turns out that we can quickly get a good estimate of the true gradient nabla C, and this helps speed up the gradient descent and thus learning. So we can bypass the difficult for huge number of mathematical operations. So the algorithm of action is the following. Let us now choose, yes, labeling random training inputs, x1, etc., xm, and refer them as a mini batch. So let us randomly choose some mini batches. Choose the sample size m large enough for which the average value of delta nabla C xj is approximately near close to the value of nabla Cx. That is the, you see, the summation on the small batches divided by m is near by value as the summation of nabla Cx on all training sets, which can be very big, huge number, and it is about nabla C. So gradient of our cost function, where the second sum is over the entire set of the training data. So it is inobservable, but it is very simple. So we can expect that nabla C is something like the middle value of nabla Cxj, so on small batches. Hence, we can estimate the overall gradient by computing gradient just for the randomly chosen mini batch. Returning to our task and training with those mini batches, we have the adjustment procedure, yes? So we have consequently such iteration, wk, substitute to wk minus our correction, our gradient correction, and BL also, gradient correction. Now by very small training batch. Okay, where the sums are all the training example xj in the current mini batch. Okay, for example, if we have a training set of the size 60,000 as the data set of American Institute of Standardization, so and choose a mini batch, say of 10, this means that we have get a factor of 6,000 speed up in estimated the gradient. We'll get a factor of 6,000 speed. It is the same. It is the same. So today a well-turned neural network outperforms any other known technology in the solution of recognized handwritten digits and record the record of 2030, correctly classified 9,979 out of 10,000 images. It is it is something like 3% of error. And the level of accuracy is close to and perhaps even better than human, since several images for this data set are difficult to decipher, to appropriate even for a human. For example, such handwritten, which easily recognized by neural net, but for a human is big problem. Some preliminaries for the next consideration on deep learning. Let's say we want to determine if a person's face is in an image, this, and this. So we have some common elements of these three photos, but only one of these photos present a person's face. So the problem can be approached in the same way as handwriting recognition, using image pixels as input to the neural network, and the output of the neural network will be one neuron will say, yes, it is this is a face, and other no, this is not a face. So we have need only one output neuron. How to build the necessary neural net for such a purpose? It can be, and it is done by segmentation of the task. The heuristic says that if we can solve sub-problems using neural network, then perhaps we can create a neural network for face recognition by combining several networks for more easily sub-problems. Below it is possible is a possible architecture for such a neural network. So we have some input layer, image p pixels. So we should scannerize this photo in the grayscale, okay? And then to pose the following question. Is there an eye in the top left? Then, if there an eye in the top right, then is there a nose in the middle? Then, is there a mouth at the bottom? And then, is there hair on the top? And then to elaborate this analysis in order to produce one input. Is it a face, yes or not? So in rectangles, there are subtasks of our recognition, which in turn break down into other subtasks. For example, if there an eye in the top left, then if there eyebrow, are there eyelashes? Is there an iris? So a lot of additional characteristic which accompany the the fact of an eye in the top left. And this question for on top left can be also be divided, segmented on with more problems, yes, but more simpler problem. Also for any rectangle, this rectangle. So the question 2 can be broken down further and further through multiple layers. Ultimately, we will be working with subnetworks that answer questions so simple that they can easily be answered at the level of single pixels. Of course, there is not explained how to do this recursive decomposition into subnetworks. So consider these separately or to ensemble it together. It is a problem, and there are some approach to this problem. It is not now very important. To end result, this is a network which breaks down a very complicated question. Does this image show a face or not? Into very simple questions answerable at the level of single pixels. So we decompose very complicated problem into a series of very simple problems. It does this thorough a series of many layers with early layers answering very simple and specific questions about the input image, and later layer building up a hierarchy of ever more complex and abstract concepts. Networks with this kind of many layer structure, two or more hidden layers are called deep neural networks. So when we have two or more, it is deep neural networks, and we should introduce some smart procedures of deep learning. The reason of deep neural network, of course, is the ability of deep nets to build up complex hierarchy of concept. And with deep learning, it begin really the similarity of artificial intellect. Recently, a set of technique has been developed that enable learning in deep neural nets. These deep learning techniques are based on stochastic gradient descent, which we have considered below, and back propagation, but also introduce new ideas. And the back propagation will be the argument for the next lecture, fourth lecture. For example, transformer technology announced for the future presentation. So the principle of RoboCops, yes, of transformers works also in deep learning of neural network, and the idea is to drastically to accelerate the procedure of deep learning. Okay, for today is we have finished. So unfortunately, this is the repetition of the lecture, which have not registered at the second lecture by reasons of some technical problems. So it is the second lecture without questions, unfortunately. So next way you can ask a question which you can be appear. So for today finish. Thank you for your kind attention, and see you the next lecture. Bye bye.